Hello community, let's have a little bit fun today with interactive and complex agent, the latest AI research. And if you want to be a little bit more scientific, we have this one. We are talking about PRM Qlass. And if you're saying, hey, could you please explain this? Of course, we are talking about quality guided language agent stepwise search. And we look here at new process reward models. And there's a simple goal that we have. We want to make our AI agents more intelligent. Much more intelligent for a particular task, for interactive task. You know, those agents, they take over your computer, those agents, they go shopping for you, and simply they are not intelligent enough. So especially for complex interactive tasks that an agent is performing on your computer, we have to make those agents more intelligent. Welcome to my video, so great that you are here. So let's start. The authors here, we have a new scientific study. They examine here online shopping, household tasks. So we are talking about pure robotic implementation and even scientific experiments. And you might say, hey, wow. So the agent goes out in the world and does scientific experiments. Isn't this fascinating? Now, we have here a very particular situation where for each step that the AI agent performs autonomously, it needs a step-by-step wisdom. So it needs here a guide, if you want, whispering here into the ear of the agent at every decision point here, something what we call a wisdom, some advice, something that was learned so that the poor agent makes here the better decisions. And therefore, there's this new framework, this Qlass, or quality guided language agent stepwise search functionality. We're here looking for more performance in complex interactive tasks, and let's start. Of course, we are not talking here about training time optimization. We are going here at inference time search. No? We want to increase the efficiency and the effectiveness using here a particular process reward model quality guidance factor that I'm going to show you. And we train a new neural network. We call this a Qnet, a quality network. This is the little whisperer to our agent. This is the companion to our AI agent that has the knowledge how to do this. And this Qnet provides here guidance for the action selection at each and every step during here the inference. So you remember here our reward model here for the state and the action and the reward calculation. This is exactly what we look for. And we have an intelligent companion that will help us to do this in inference time compute. So let's open up the arena and have a look. Yes, exactly. This is where we are. From my last video, I showed you here, we were looking here at non-TTC models. And then we will look here at the O1, this inference time reasoning models. And you see here, if you scale here the hidden thinking tokens, or scale here the chain of thought tokens, our performance just significantly jumps up if we look at one of our two complexity measures. And the first one was the search space size here from the video. So we're exactly looking here to push this up to have an inference time optimization that is even stronger than this one. Now you know the classical picture. In the classical traditional approach by our grandfathers, we had the outcome reward. A very simple score at the very end if we have got the final solution. But this is not enough for us, because if those agents are interactive somewhere with your credit card, you don't want to wait till you get here the bill of your credit card a month later. So this outcome reward, no way that we're gonna work with this, because then the agent end up wandering in a vast internet online search spaces, making inefficient choices. And whenever you read as a scientist says, making inefficient choices, you know, this is not what you want from your AI agent. Now let's have a look at our beautiful LLM that does here is the heart of each and every agent. So we have here a pre-trained model, then we supervised fine-tuned it, then we had here the reinforcement learning, the DPO. And now here with this, we are now online with a query. We have the test time computer, the inference reasoning happening now. And as I showed you, if you wait 2 to 5 minutes, in the inference run now this happened that the system tries to find here reasoning paths to arrive at a final answer given my query. This is the solution to my query. And of course, we have here exploration and exploitation. So this means multiple pathways to the solution will be explored, and a different depth here. There will be the reasoning depth that the LLM will compute for arriving at the final answer. And of course, as I showed you in, I don't know, 5 or 10 videos here, we will use Monte Carlo tree search here. So we build here branching trees of possibilities. And in the classical system, with the final reward signal at the end of the thinking, we then have this classical Monte Carlo tree search, backpropagation, great, but this is something that we have to improve today. So think of this, hey, you're a student, no? And at the end of the semester, you have one final test. And this final test, in these 2 hours, your whole whatever will be challenged, and you will decide here your future professional career. So this is not what we want, because if our little AI agents are out in the wild on the internet with your credit card, you don't want to wait to the end of the semester. So we need a little spark of genius right now, and no problem, we have multiple sparks. Just remember here my very last video where I showed you that Stanford University developed like O1 or Open or DeepSeek R1 S1, hello Stanford, model. And what they did, they had simply here a hyperparameter, and they said, listen, after, I don't know, a certain amount of tokens, 500 tokens, 1000 tokens, I just tell it, hey, stop. You don't continue here with your reasoning path. This is it, this is the end, now you give me your final answer. And then maybe you have to put this in a manual hyperparameter. You can say, go on for one step, you know, this weight parameter that I showed you here in my S1 video. And then maybe it's allowed to go another 1000 tokens. Now the effect is, as I showed you already here in the S1 video, if we have an R1, for example, that generates here for an incorrect response 7,000 or 10,000 hidden thinking tokens, this are all for nothing, because we do not arrive here at a solution. But look in the green, these are the ones that are valuable. No? This is the correct pathway in the reasoning. These 2,883 tokens, those are the ones that we want to have. So this idea by Stanford S1, working here with manual hyperparameters, was successful, especially if we have here a run. Let's say the LLM goes crazy and generates 10,000 incorrect here. There's nothing green as you see here. Incorrect hidden reasoning token and does not arrive at the final answer. Everything is here red. Then the system failed, and with this S1 threshold after, let's say, 500 token or 1000 token, you can stop the machine of going crazy ad infinitum in a loop. So, nice idea by S1, but we have now to develop this further. So, first idea was we wait for the final answer, you know, at the end of the semester. Then, with Stanford University, hey, after a manual threshold of token, let's say 1000 token or 10,000 token, I order the machine to stop and I look at the result. But now we have to go to the next step. Now we have to have the new idea, and yes, I presented it already to you. Now we go, and after each decision that here our LLM, our AI system will do, we will have a process reward model calculating here the future discounted reward structure in our Monte Carlo tree search. So what we will build for our agent here is an internal step-by-step. So for each step, reasoning step that the LLM is doing is hidden token process. We will have a process reward model, a dynamically adaptive process reward model. So we don't wait till the end. We have no final benchmark here, a manual hyperparameter. We will do this at every block step or every reasoning step. But you might say, but how can we calculate a reward if we don't have here a final answer? And the authors of the study I'm going to show you, they had a beautiful idea about a process reward model that is really here interacting here at each and every step here of our reasoning token. So what we have our classical Monte Carlo tree search and a new process reward model. And you might say, hey, wait a minute. About 1 or 2 weeks ago, I did here a video where I showed you here a new methodology called R star This is for mathematical causal reasoning by Microsoft, and they coded here a self-evolution LLM. And you know what? If you can remember my video, if you are a subscriber to my channel, hello subscriber, we also had a Monte Carlo tree search and a process reward model. So the idea was already there for some weeks ago, but now we don't implement it only for mathematical reasoning, but now in a more general pattern. So let's come here to the core of the video. What we want to build? We want to build some dynamic and adaptive AI agents you can send them off for online shopping. You just give those agents your credit card and you hope that the intelligence of those agents is extraordinary. Otherwise, you are in deep trouble. So what we need? As I told you, we need an intelligent companion to our AI agent. We need an intelligent Q network. And you remember we had in the good old times here, we had our LLM and then we had those RAG system, those retrieval augmented system. If you wanted, it's a little bit parallel. Now we have our AI agent with the LLM. It's the heart of this agent. But now this little fellow needs here a companion. The agent needs here a Qnet system. Let's do this. Qnet assesses now the quality of each action that our agent is doing out there in the wild with your credit card at each decision step, at each reasoning step, based on the potential, like this little Qnet thinks, will contribute to the long-term success. So, although it is a step-by-step decision, the focus in the calculation of the reward is the long-term success. So think of it as a highly insightful coach, if you want, for our AI agent, constantly evaluating each and every move of our agent and guiding here the agent for every move. You know, it's like, hey, isn't this crazy? We have an agent, no? Should not be the agent intelligent? And now this intelligent agent has an intelligent companion because the agent is not intelligent enough if we send him free with a credit card on the internet. Welcome to AI research. So, this Q function, you know, for Q and Q star, we have it for 2-3 years now. This is the quality function. And this is, people ask me how to explain this. Look, this is easy. Just answer this question. If the agent is in a particular state, has already done some shopping for you, and now it takes a specific action, like to buy here a very expensive PC for you. How good is that action in terms of achieving the overall goal in the long run? So you see, we have the state that the agent is in, and we are looking now at a specific action that the agent might do. And then this Q function here has a particular input. This is simply the state of the agent and the action. For example, search for whatever, or click at this item, buy this item, whatever. And the output now of this Q function, and it will become much more complex in 5 minutes time, is now a simple scalar value, a Q value, a quality value. This is a simple number, could be even more difficult, but let's stay simple, a single simple number that represents the expected future reward. If the agent starts in the state S, takes an action A, and then continues to act optimally from then on. And you might say, how the heck can we calculate the expected future reward function? We don't know the future. Yes, but we have knowledge from the past. And you see, we calculate the future knowing what happened and how we solved topics in the past. So this future, if you want, is kind of a limited future on the known facts of the universe. Okay, let's do this. Now, if we are now in the real world now, and we have now language agents and to do some web shopping and scientific world and whatever, the real Q function, the real complexity, what they could do theoretically, this is incredibly complex. We have no idea about 15 steps into a reasoning chain, into an action chain. Where will they be? On what web page will they be? What will have they bought? So We can't know this. So it's impossible to create a simple table that lists here out here the real Q values for every possible state action pair, because there are just too many. And this is now where our neural networks come in. No? It's a powerful tool to approximate complex function. We say, hey, this is a complex function. We take a little neural network, we take a little transformer, we have a little MLP head on top of it. And you know what? With a softmax function here, a ReLU function, we get a scalar, and this is all what we want. So we build ourselves a little intelligent companion that we call Qnet. Now, the mathematical detail I skip here because I just wanted we have fun in this video, but you could think Qnet as a function approximator. It is a neural network, a transformer network, that learns to take here the particular state S, so all the history of your agent, what the agent already did on the internet and bought on the internet, and now this particular action A as an input and outputs now an estimated Q value, Q dash. And this estimated Q value is of course only an approximation because we do not know the true Q value from the pure theoretical mathematical Q function. How we do this? Well, easy, we are in AI, no? So we have an LLM, beautiful. The LLM acts here as the agent policy, and then we just add here a value head. So multi-layer perceptron, this is it. The value head takes the LLM internal representation of the state and the action and processes them into a single number, the Q value estimate. That's it. Now, unfortunately, in the study I'm going to show you in a minute, they used here a Llama 2 7B model. My goodness, authors at the university, please, why are you working with models that stopped to exist years ago? I know it's dirt cheap, but please, come on. The whole quality of this beautiful idea hangs here that even my Llama 2 is able to do some reasoning. So, okay, I get it that financial resources are limited, but please don't go with a Llama 2 model. Okay, anyway, MLP, easy to hidden layers, size of 1024, and we have a non-linear ReLU activation function. This is it. So, of course, now the main question is, if you followed me up until now, congratulations, by the way, how does now our little Qnet, our little companion to the AI agent, learns to predict this particular quality values? Now, easy. It's a neural network, so what we do, we train it using supervised learning, supervised fine-tuning from Hugging Face, no? So, at first, we need a data set, so we do a data collection. You say, hey, that is easy, because we have exploration trees on Monte Carlo tree search, yeah. So we use this Monte Carlo tree search to build our exploration trees and estimate here Q values for particular state action pairs within those trees. And those estimated Q values become now the training target for the Qnet. Then, if we have the data set, what we do? Simple. We have a supervised training from the exploration tree, and Q is the estimated Q value of that pair, and we will calculate this using the Bellman equation. I'll show you this in a minute. Simply Monte Carlo tree search backprop, the classical way. And then, whatever we do, we have a loss minimization. We do the same here for this transformer network, for this Qnet is trained to minimize here the mean square error loss function, or if you go with another loss function, beautiful, between its predicted Q values and the target Q values from the dataset. And this forces here the Qnet network to learn here to approximate the Q function that was estimated here in the very beginning here through the Monte Carlo tree search. So you see, a simple idea, and we use all the tools that we know from the classical AI. Now, careful for the action scoring, the scoring value during the inference run. As I told you, careful, this agent is now shopping like crazy in the internet. So when our language agent is performing a task in the real environment, so now at each step, it can consider multiple possible actions. No? Imagine a web page. Now the agent could click on all the different links that are on this web page. So for each candidate action, it uses now the trained Qnet companion to calculate here the predicted Q value. If you want to buy a bike, a bicycle, then this is your goal, and then everything that the Qnet decide, yeah, if we see here an image of a bike, then we click on this image of a bike, and we hope that then we will go to the next web page where we are able to buy a bike. So the predicted Q value for this particular image will be real high compared to all the other links on this homepage. And then the action selection, well, this is simple. The agent then chooses the action that has the highest predicted quality value according to our little companion, the Qnet. And all of this is now called the Q-guided generation. So the Qnet guides here the agent towards action that are predicted to be more valuable in the long run. You would really buy your bicycle online. Great. Now, if you think, hey, if I'm in this situation, so I'm in this particular state, and I take this action, says now my little LLM, my agent, what is my overall chance of success and reward in the future? So let's put here our finger really here where it hurts and said, how do we want to calculate the reward in the future if we have a lot of possible trees available in front of us and branches and leaves available? How can we calculate here discounted futuristic rewards? Now, you know, in the classical AI way for generations, we have the Bellman equation. This provides here a recursive way to define here the optimal Q value. And this is what you learned in computer science whenever you studied here mathematics, physics, chemistry, whatever. Beautiful. I hope you remember this. And our gamma here is discount future rewards. Now, in our particular methodology, it doesn't directly solve for the optimal Q function, no Q star. It estimates here the Q values using here the Monte Carlo exploration tree and a slightly modified version because remember, we don't run with expectation and everything because we really do calculate this. So our equation becomes a little bit different for all the action at the time t plus 1 in the set c at the time t. You remember that the classical Bellman equation has here this expectation here because the environment might be stochastic. But in our current mathematical formulation, we are working here with deterministic environments. We have here a homepage exactly with 4 buttons I could press or the agent could press to buy a bicycle. So there's no need for this expectation, and the next state, S for state at the time t plus 1, is simply determined by the action A at the time t. We have a max operation, but this is the classical one. We have then the recursive calculation of the Q values are calculated recursively, starting here from the end leaf nodes of the exploration tree. You know this. And finally, we have a min-max normalization so that everything of our Q value scales beautifully between 0 and 1 or minus 1 and plus 1, whatever you like. So this is now important. Please careful. So in our new methodology, we use now the Bellman equation as a tool to distill the sparse outcome rewards into, you remember the outcome rewards, the end final rewards, into some dense, stepwise Q values of our reasoning chain. Leveraging the structure of the exploration tree to guide this process. So suddenly we have stepwise Q values for our process after the learning phase and everything. And they are not here sparse outcome, their final reward, but we have dense step-by-step Q values. And this is now the beauty. This is now what we wanted. So the Qnet then learns to predict those distilled Q values, then stepwise, providing now, learned as a neural network, a powerful signal for guiding now the agent actions during the inference run. So this Qnet is now trained, is now intelligent, and is the companion right next to the AI agent when the AI agent is scanning here the internet and wants to buy you a bicycle. Because Qnet knows now exactly the successful way how to guide or operate here the free internet. Just want to stress this again. This is because we are here, the agent is running free here in the internet. We have to make decisions that are not at the starting point, at the final end point. And we say, yeah, there should be here a connectome. No, we have to go step by step. every link on every homepage that could theoretically be clicked by our agent, and the agent would buy some nonsense, we have to be aware and we have to tell the agent, hey, you do not click this link, you do not click this link, you look for the link with the highest Q value approximated. Yeah, multi-colored research is used to explore the multiple potential actions, creating here a branching tree of the possibilities. We talked about this. You could see this little intelligent, the Qnet here, as a local guide here for the agent. No? So the Qnet is used at each node here in the Monte Carlo tree to score the candidate actions available at that specific particular point. And careful, it is not pre-calculating now a distant future. It is not pre-calculating a global planning, but just providing local guidance for each decision that our AI agent might or actually will perform. So the Q values predicted now by the Qnet represented the estimated long-term value for our goal, buying on the internet a bicycle. Great. Okay, let's come now to the simple facts. It's a beautiful paper, February 4th, 2025, by University of California in Shanghai, Jiaotong University. A beautiful cooperation, highly interesting paper. If you have the time, please read this. There are a lot more details, but I wanted to make it here fun today in this video. I wanted to keep it simple, but also to be precise and give you all the detailed background. But now with this introduction, I think you should really enjoy reading this paper. I'm doing this just hours after it was released. So they say, hey, we will release the code, the checkpoint, and the data for this. So if you go to the GitHub repo here on Qlass, maybe you are logged in, you have already the code and the data there. For me, it is simply too early. And if you want now a summary, you say, okay, let's have here the 10,000 feet overview. Either you go here with the pseudocode and you have here 4 steps or whatever you call it. So you have your cloning, you have your reasoning tree that you build up with the multi-colored research. Then you have your Qnet training phase and then the Qnet guided generation of the decisions for the state action at each step of the agent. Or if you want, I have written it down out for you. So this is now really simple. Let's start. The first step is here, the supervised fine-tuning. We have to start somewhere, no? And now it begins by building here a foundation using here the supervised fine-tuning, and we take here a base language model and we train this to mimic here some expert behavior on a data set of successful task trajectory. We just recorded here the last 10,000 internet buys of a bicycle. So this creates now an initial capable agent policy. How to do this, how to define the actions. Then we have to build our exploration trees. So in order to understand the task landscape, we employ now the classical Monte Carlo tree search algorithm to construct our exploration trees. And the AI agent, guided now by its new supervised fine-tuned trained policy, explores now the different action sequences, branching out at each single step. So each path in the tree represents here a potential trajectory of interaction. And within this exploration tree now, we have to estimate here the quality values for each and every state action pair. So drawing now from the classical reinforcement learning principle and our Bellman equation, we calculate now these values based on expected future reward discounted associated with each action. Beautiful. Steps that consistently lead to successful outcomes are assigned a higher value, and this is how we do encode here the wisdom in our little companion Qnet for the agent. And then the heart of the Qnet is, of course, the training phase. So this neural network, this transformer network with this particular head here, architected a transformer backbone with a MLP head, value head, is now trained also in a supervised manner, and it learns simply to predict the Q values estimated here in the exploration trees. So this Qnet essentially learns to internalize here the historic knowledge, the historic wisdom here of the other Monte Carlo tree search exploration processes and learn from this. And then we have our little trained Qnet. Now our companion is ready to be operational. And then we said, okay, finally, we have here the quality guided generation. So the trained Qnet becomes now active for the agent. And the agent can now listen to the recommendations by the Qnet, because Qnet calculates here the quality, the scores, the rewards for doing here a particular action out of a set of possible actions. So at each step of a new task, the agent considers multiple action, uses here Qnet to score each action based on its predicted quality value, and then the agent select here a particular action, and yeah, you can say with the highest quality score. And we have stepwise guidance during this inference. Remember, we're here time critical in the inference run, maybe 1-2 minutes, making now the decision more targeted and efficient to buy here from some web pages some stuff. If you would like to see here the relevance to the classical terms that we use normally in AI, so we have our Qnet here as the reward model. Qlass here trains here the Qnet to directly predict here the approximated Q values. And this is our classical process reward model. It's used online during the inference, as I told you, to guide here the action selection by the active agent that is already out there with your credit card on the internet. And then to calculation itself are done here by the classical Bellman equation that are a little bit optimized here for the Q value target within the Monte Carlo tree search. And you see, this is it. This is all there is to this paper. Yeah, and this paper evaluated then, of course, here the performance, and it did here a complex interactive task by our agent. And we have here the classical three, the web shop, AlphaWorld, and SciWorld for a scientific experiment. And what a surprise, the authors tell us then at the end here, this has a superior performance. So this new methodology, according to the authors of the study, consistently outperforms here strong baselines, including supervised fine-tuning, PPO, best of n, and even surpasses here GPT-4. Imagine a Llama 2 decision model, a reasoning model, surpasses here GPT-4 on all three benchmarks. And they tell us, hey, this demonstrated the effectiveness of a Q-guided stepwise search. Yeah, but it would be nice if you do not have a Llama 2 model as your core LLM. Because, yeah, you get it. Second, inference time efficiency. Remember, we only have 1 or 2 minutes that we are waiting for the response from this thinking LLMs. Now the authors tell us, hey, this new methodology achieves a better performance with fewer search tokens. Remember, 10,000, 17,000 search tokens that are hidden, maybe just wasted. Fewer than the best of n methodology. And the authors tell us, hey, this is a more efficient way to improve here inference time performance of reasoning models, where this LLMs are the heart of AI agent, and this AI agent is out in the wild with your credit card to do some shopping. Let's come back where we started. So remember I told you about R-star mathematics from Microsoft that also used the Monte Carlo tree search and this process reward model and everything. But let's make it clear now that we know exactly what Qlass as a methodology is. It is simply about making AI agent act smarter. Now in the inference run, in the test time compute, in this 1 or 2 minutes that I have already given it my query, my task. While if you watch here my video on R-star mathematics, this is about self-learning models. So the models learn to reason better over time. They are learning how to improve themselves through a very similar methodology to a carefully crafted self-improvement loop, but all the details you find here in my other video on R-star. So there you have it. I hope you enjoyed this video. I hope you had a little bit of fun. It was really interesting to prepare this video because I wanted to spare you with all the complex mathematical equation here. I just wanted to give you the main idea, that you get a feeling for this, that you say, yes, I enjoy working with AI agents. I understand how we can improve them. And this is a beautiful methodology to improve your AI agent if they're out there in the wild. Because believe me, if they are here wandering around with your credit card, you want to make sure that this agent is really a brilliant agent and is only performing necessary steps in the internet with your credit card. So therefore, If you would like to subscribe, hey, it would be great to see you in my next video.